Okay, let's get started. Welcome to CS 11747. So today I'm in charge of the class, and I'm going to talk about the convolutional networks for the text. Here is the general outline, detailed outline of this class. And first of all, I will review some content we have discussed in previous class. Also introduce the feature combination, the concept. And then we will introduce some basics of the convolution operation. So after we have know some basics concepts, we should maybe conduct a study on a specific natural language processing task. Here, I choose a sentiment classification task to know how to apply a CNN in a real-world task. Then I will introduce some convolutional networks, variants, and its corresponding application. Finally, some extension of the vanilla convolutional network will be introduced, such as the structured CNN, some tree or graph CS. If I still have the time, I also would make some summaries of this class based on my understanding. Maybe I can continue. I think everyone here will remember these examples. Actually, Graham has introduced this sentence in several times. It is a very simple task in natural language processing. We call it the sentiment classification. And here you will have a sentence, and the goal is you should predict a sentiment score for this sentence. For example, here we have these two sentences. And I think this task is very easy for the people, right? Because the times we have seen the hat, the word hat, we know it is a very negative emotion. The times we have seen the word love, we know it is a positive emotion. So it's very easy for us to do this task. So the question is, how does our machine to do this task? And the solution is also not very difficult, because here is one of the simplest method. We call it the continuous step of the words, the CBOW. So the basic idea of this method is, given a sequence of words, you should convert each word into a distributed representation, or it is a dense vector. So you should refer to a lookup table. If you have the lookup table, you can convert each discrete signal to a distributed representation, and then you can average all the vectors. You will get finally you will get a sentence level vector, and this vector could be used to represent the sentence level semantics, and you can use the vector to do anything you want to do, such as the sentiment classification. And here is an easy extension of the CBOW. We call it the deep CBOW. And the major difference of this model is that you could introduce more linear transformation followed by a nonlinear activation function. So usually when you get the representation here, and you could add more linear transformation here. So I have noticed that usually this model is more powerful, but it is not a guarantee that you could obtain better performance compared with the previous model. Some students have posed a question, that is, why my deep CBOW model cannot obtain a better performance. I think it's reasonable, because sometimes this model just introduces more parameters, and your model suffers from some overfitting problems. So you should maybe you should check if your data set is not too large, and you should introduce some dropout mechanism to overcome this problem. So let's see what's the use of the deep. So the deep usually could help us to capture some hierarchical structure, such as if we use the deep CBOW, we could capture some patterns such as a knot and head. But this model cannot deal with the pattern, not head. So one question is how to deal with this problem. There are also very easy models. I call it bag of n-gram. So here the n-gram means the n-gram actually it is a contiguous sequence of words. So compared with the bag of word, here's the difference is the unit you processed is not a word, but a text span or a contiguous of words. So you could model the combination of the different words. Then you can your model will be more powerful. Here another question is suppose given a sentence. Previously we could use I had these two words separately. Now if we use the bigram, you will have I had and all the had this or this model. This would be the basic unit. And the question is how to represent the two words together. Usually, we just could concatenate the word vectors into a Unicode vector. Then you can, it is a very simple idea to represent the text span representation. So here is just something you should pay attention to. So why we use the bag of n-gram? So actually, if you have to do some research in natural language processing, you will find bag of n-grams is a very decent baseline because in most of the cases, this baseline is more competitive, especially when your text is too long, such as a long document. This baseline can even outperform the LSTM, the CNN. So it is when you would like to process a text, you can implement this baseline first because it is a very decent baseline and it really could work very well. So let's see what's the advantage, disadvantage of the bag of n-grams. Here there are just highlight 3 points. The first is it suffers from the parameters exploring problem, and the second, no sharing between the similar n-grams. So the first and the second disadvantage is because if we use n-gram models, we usually need introduce the multi-layer perception layers. So the different n-grams, different granularity n-grams would require different types of parameters. So they suffer from the first and the second problem. And the third problem is very normal because you use a bag of words, bag of n-grams, so they just lose the global sequence order. So here a question is, are there any other solution? Yes, we should have some solution. Otherwise, maybe the class is over. So what's the solution here? Here, I think the time is right for us to introduce our leading rules in this class. So here I want to introduce a concept called neural sequence model. Actually, for the neural sequence model, the thing is given a sequence of words and characters. You should design a convolution function, and the goal is you should convert a sequence of words into a fixed dense vector. So also, if you have to do some NLP research, you will find most of NLP tasks could be reformulated as this this question, I mean, the representation of a sequence. Here is a concrete example. Maybe the input could be a sequence of characters, impossible, and or a sequence of words, like this movie. So next you would have plenty of a bunch of choices for you to compose the input information, such as the CBOW. We have introduced also the back of engrams and the convolutional networks are the transformer or the graph network. So for this class, yeah, the convolutional network is our leading role. So next, let's get into the details of the convolutional neural networks. If you have chosen the teaching class such as the signal processing, you will find as the convolution is a mathematical operation on two types of function. And generally, the operation could be classified into two types: the continuous version and the discrete version. And it's not very difficult, and you could find what the convolution operation has done. So for the continuous version, it is defined as the integral of two functions products. And in natural language processing or even the computer vision, most of the input signal are discrete. So we should focus more on the discrete version of a convolution. So it is defined as the summation of two functions product. And usually in the deep learning, in the neural network, which it is not necessary to reverse the function f. So it is the final version we used in our convolutional neural networks. And no worry about this equation because we only have these three equations in our class. And the next, I will give an intuitive example of this equation. So as you could see, the function f here is the function f is and the function g is two vectors, and then each cell in the green box, each value in the green box could be calculated by calculating the summation of the two cells product in the f and the g. So and in deep neural network, the function f usually can be regarded as the input, and the function g usually is regarded as the filter. We also call it something like the kernel. And the parameters of the filter should be learned. That is the convolutional parameters. And the result usually be regarded as the output or the hidden data. So taking the neural network's view, we could understanding this equation. Just the input is a feature vector, then you have some transformation filter, and then you could get the output. So here I just want to raise a question. That is, what types of priori entailed by the convolutional neural networks? As you can see from this figure, here are just instantiate of the f as different words, the W1, W2, and W7. So the first priori entailed by the convolutional network is the local bias. It means the different words could interact with the close numbers. So what does it mean? It means if you have chosen the convolution neural networks, then you just use assumption. That is, the local information would be heavily used in your network. So that's the first priori. And the next is parameter sharing. So you will find all the subparts of the input vector f just share the same parameters. I mean, share the same filters. So that is mean if you use the convolutional network as your model, you also just make assumption that is the the composition of the different words can be learned with the same parameters. Here I just want to highlight these two types of priori because in later slides we also use this to point to explain something. In what follows, I will introduce some basics of the convolution neural networks. The first is there are very simple concepts. The first is from 1D to 2D convolution, and so you know, especially in some computer vision area, we should process the image. So a very easy extension is from the 1D to 2D. So the input vector f would be the two-dimension matrix, and the future also would be a matrix. So the output hidden vector also would be a matrix. So the thing you do is just the dimension is from the 1D to 2D, and the other thing just follows the 1D definition. So the next concept is the stride. The stride is very easy, just defined as the number of units shift over the input vectors. Here you can see this figure just shows the case of stride size equal 1. So you will find the window slides one step or one unit at one time. So how about this case? This case just shows the stride size equals 2. Yeah. So these two slides just show there is a concept called the stride in the convolutional network, and how to decide the stride size is up to you. Another concept here we call it the penning. So previously we used the figure to illustrate the convolution process, and you will find there are some problem in this figure. That is, the output vector's length is less than the input vector's length. So in many natural language processing tasks, in many NLP tasks, we should maintain the output length equals with the input length, such as the NER problem and the post-tagging. So how to solve this problem? There is a very easy solution that is use the pending technique. We just introduce some extra elements to the input vector, such as the zero pending, which are added to 0 at the beginning and the end of the vector. Then we also conduct the set convolutional operation. You will find the output length is equal to the input length. So according to the different pending mechanism, we also could define the different types of the convolution operation. The first convolution types of the convolution we call it the narrow. So the characteristics of the narrow convolution is usually there is no pending mechanism, and the output vector length is less than the input vector length. And we also have another types of convolution, we call it the equal. So you also can find its characteristics. The output, because we have used the zero pending mechanism, and we could maintain the output vector length similar to the same as the input vector length. So what's the next? As you can guess it, that is the wide convolution. So in some other case, we also should we just want to make full use of the input vector's information. So we make more pending element, and then we could the output vector length could be more than the input vector length usually. just follow this equation. So this just said if you choose different types of the convolution, different types of the painting mechanism, you will get the different lengths of your output vector. It depends on the different case you have encountered with. Okay, here is a very simple idea. That is, previously all the convolution we introduced is we just use the one filter. Actually, we could introduce more filter because it would increase the capacity of our convolution networks, and you can get an intuitive understanding of the functionality of the two filters. Maybe one filter is used to capture some emotion words. Another filter is used to capture some opinion words. So they just used to capture different types of features. Another concept is also very easy to understand. We call it the pooling. So the pooling. So in natural language processing, in most of the time you should conduct an operation. We call it aggregation. So pooling is a typical aggregation operation, and why we use pooling? Because we want to get some more informative information, and in some other cases we also want to solve the variable length problem. So typically we have many pooling mechanisms, ranging from the max pooling, the average pooling, or even the K-max pooling. So, but in most of the time, I think the top two, the max pooling and the average pooling, we use them more frequently. Here I just want to make a brief illustration of this pooling mechanism. So for the max pooling, it is very easy. So given a vector, the max pooling says we just choose the cell with the highest value. So the mean pooling just there, we also want to choose one element from the input vector, and the value is an average of the input vectors. So for the K-max pooling, actually here is the K is an hyperparameters, and here the K equals 2. We set the K as 2, and the two max pooling just says we should choose two elements, and the value is the top two highest value of the input vectors. So how about last is the dynamic pooling. So the dynamic pooling we also should set a hyperparameter K beforehand. And the first thing we should do is we should partition the input vector into different groups. And for each group, we could select the maximum value. So here we just partition the input vector into 3 groups, and for each group, we choose one maximum value. That is the dynamic pooling. So if you have forget some definition of this pooling, you can refer to this figure to help you know more detail about this. Next, so previously we have know the basic concept of the convolutional neural network. So why not try to use this on a specific NLP task, and just want to show how we could use it to set up an NLP problem. It is so actually this introduction is this paper is just from the 2015. It's a very typical papers. I think everyone could have a careful reading of this. And the task also is a sentiment classification. The input is a sentence, and the output is a class level. Usually, involve the positive and the negative this binary class level. And the general framework is an embedding layer, multi-channel CNN layer, and the pooling layer. Here is an overview of this architecture. You will find maybe this is the input. So suppose we have a sentence, I love this movie very much. We have first thing we should construct the input matrix, and here is the filter. The filter means this matrix are learnable parameters, are the part of the parameters of the network. So this is the pooling. This is the pooling result. Then we have the output and the binary things. I will introduce the component of this one by one. So here is the illustration of the embedding layer. So the functionality of the embedding layer is given a discrete sequence of word. We should convert this discrete signal to a maybe continuous vector. And if you would like to achieve this, you usually should refer to a lookup table. We call it embedding matrix. So, and if you have implement some code, you will find you really should set up a lookup table, and the rule is just could convert the words into a dense vector. And usually you also could either random initialize this table or pre-train the table by some external unsupervised embedding, such as the one-to vector or the globe. So that's the functionality of the embedding layer. So then follows is the convolutional layer. So it's also very a very simple things. Here is the input matrix, and here is the parameters of the filter, and here is the output of the convolutional operation. We also could regard it as the hidden vector. So here are some questions. Maybe the first is what's the stride size? I think if you have compared the output vector length with the input dimension, you will find the stride size is 1. Stride size is 1, and the next question is also is wide, equal, or narrow convolution? Yeah, actually it's a narrow, because you will find the input. There are totally 7 rows in the input, and you can also compare the dimension of the different metrics. You will find it is 1. So how many filters? Yeah, there are 4 filters. So here is the illustration of the filters, also called the parameters of the filters, and you find the filters with a different dimension is because we want to capture the different granularity of the filter dimension. Maybe this is used to capture the trigram information. This is used to capture the quadrigram information. As for the pooling layers, yeah, I think this is not much thing to explain. It's very easy, right? Pooling layer. So since we have 4 filters, then for each filters we can get a corresponding hidden vector. I mean, for filters, then we have 4 groups of hidden vector. So for each groups of hidden vector, we can conduct a pooling operation. So maybe for the first group, the maximum value is 2, then we just put 2 here. Then the next one, the second one is the maximum number is 3, then put 3 here. Then here is 2, and here is 7. So we have, after the max pooling operation, we concatenate all the results together. Then we have a hidden vector with the dimensions 4. And this yellow vector can be used to represent the whole semantics of the input sentence. So the functionality of upper layer is just use this feature vector to make the prediction what the semantics of the sentence is. And usually, if you want to improve the performance, you also could introduce some dropout mechanism, maybe after the feature vector. You could use some dropout mechanism to improve the performance, also followed by the software mix to normalize your predict scores.
Would you add dropouts also before the convolution?
So basically, we could add the dropout after the feature vector. So usually, suppose here we have got obtained the feature vector, then we should use we should feed the vector to a multi-layer perception and NLP layer. Then after the NLP layer, you could conduct the dropout. Yeah, because usually the multi-layer perception usually contains a lot of parameters suffering from the overfitting problem. Then you should introduce the dropout. Yeah, that's it. Maybe also can, so some follow-up works also show that you also can introduce the dropout mechanism on the embedding layer. Yeah, you also can do this. If you also want to introduce the dropout on the convolution layer, you also have some help. But most of the time, we put the dropout here as last here.
Is there any reason to use different window lengths for that logic?
You mean?
Some that are false, some that are right?
Yeah. It's very similar like the to capture some n-gram information, right? Yeah, that's it. That's it. Maybe previously we said we have the back of n-gram mechanism. So here here the window size is different. It's because we also want to capture the different granularity of the combination features. You also can introduce some maybe two. Yeah, let's just capture we would like to capture the bigram information. Yeah. Any questions? Okay, I think that's a very simple framework of the convolutional network. If you also want to apply this to any other NLP task, the things is maybe you just change it after layer. If you want to conduct some semantic matching task, you should change the after layer to some other loss functions and something else. If you here just you can get the thing, you can get the information is here is show how built up your encoder use the convolutional unit works. In what follows, I would like to first introduce some CNN's variants. So here is an interesting thing. That is, previously I have said that for the convolutional network, we have highlighted 2 points. That is, Prioris intended by the CNN. The first is local bias. The second is parameter sharing. So here follows 2 questions. The first is how to handle long-term dependency. So because we have said the CNN focuses more information of the neighbors, the close neighbors. But what if we want to capture some remote neighbors or some long-term information? That would be one question. So another question is how to handle the different types of conversationality. I mean, for the vanilla convolutional neural networks, the conversation of the different words are learned based on only one or sharing parameters. What if the conversationality is too complicated? I think maybe the only parameter sharing is not enough. So here I just want to claim that the priori entailed by your network somehow it could be one type kind of advantage of your model. It also could be a kind of potential limitation of your models. So that's what the future work, most of the future work has done. So based on these two potential limitations, they proposed a different solution accordingly. So maybe because the CNN focus more on the local information, we should introduce some long-term dependency mechanism, and the solution is maybe increasing the increase receptive field. So that's the first point. The second is, since the CNN is based on assumption that is parameter sharing, so what if more complicated interaction come? So the solution is we could use some dynamic filters. Here are concrete examples. So this work is used too. So the motivation of this paper is to introduce, they would like to the CNN to capture more long-term dependency. So they use the technique called it the dilated convolution. Basically, the one thing they do is just gradually increase the stride layer by layer, and finally you will find the long-term dependency could be captured with relatively less layer. So maybe the last words could be interacted with the first words just by the full layers propagation. So the motivation. Sorry.
In the previous example, the stride is constant, right? Not increasing.
Sorry.
The stride is constant, right? Too.
Oh yeah, the size is it's consistent, yeah. But you should increase the strand size maybe after the next layer. Yeah. And here this work, the motivation of this work is also very simple and intuitive. So previously, the parameters of the filters of in the convolutional network work is static, right? I use the term static. So then it would be lead a problem that is maybe it's difficult for us to capture the rich interaction patterns. So one solution has been proposed in this paper is that why not try to introduce some filters whose parameters can be dynamic generated. You can see in this figure, we have the input A, and we use the input information to generate the parameters of the filter. Then we get the dynamic filter. After this, we could use a filter to convolute with the input B. So the input B also is a transformation of the input A. So it's a very interesting idea, and the basic secret of this work is they think the parameters of the filter could be sample dependent instead of the static. Yeah, that's the basic idea. So why? What's the use of it? Because if you do this, you will find your filters could be handle more complicated interaction, and your models would have the large capacity to deal with this phenomenon. So, any question about this? Any question about this work? So in what follows, I would share some common application of the convolutional network in natural language processing. So generally, I think the application of the CNN could be summarized into the two categories. The first is word level CNN and the character level CNN. So what does it mean? So the word level CNN means the signal or the unit, the basic unit will be processed at the word level. For example, we could use the convolutional network to learn the representation of a sentence or a sequence of words. So the functionality of CNN here is used to capture the phrasal level patterns. That's the word level CNN have done. So regarding the character level CNN, the basic idea is the object, the modeling object is not a word but a character. So for example, we have a long word and we want to learn the representation of this word. We could use a character level CNN. And the functionality of the character level CNN is it can be used to extract morphological patterns. It is very useful for some tasks such as the sequence labeling or some of the Chinese word segmentation. So for some fundamental tasks, the character level CNN is quite useful. So here we just give one example for the word level CNN. The paper is the natural language processing from scratch. Actually, this paper has been recognized as one of the most important papers in natural language processing. Indeed, this paper is a journal version, and it also have a corresponding conference version called a unified architecture for natural language processing in the 2008. And this paper has been has obtained the test of the time award of the CML. I think it's a very precious honor for a researcher. So this paper is highly recommended for you to read. And here is a general framework of this work. And the input is at the top of the figure. You have the input sentence, and you also should convert your sentence into a distributed representation. So you have a lookup table layer, just similar to the previous slides said the embedding layer, and then follows is a convolution layer. You should maybe convert the different word representation into contextualized representation. You use a convolution layer, followed by a polling layer, and finally you get some get a hidden vector, and this hidden vector can be used to represent the whole semantics of the input sentence. So that's the general pipeline, and this could be applied into many other works. And if you have read this paper, you will find many maybe training tricks and the details of it. Just in a word, this paper is highly recommended for you to read. So this is the application of word level CNN. Then another application is the character level CNN. Actually, it's not a text classification. It's a tagging. So what does tagging mean? So the tagging is a very fundamental task in natural language processing. Given a sentence, you should predict a label for each word of the sentence. That's the tagging should do. So here I introduce this work is because this work also provide a very general framework call it CNN-RNN and CRF. This CRC framework, and this framework currently has become a de facto standard for the tagging task. So it also worthwhile for you to implement this framework. And one thing should be noted is that you will find here the character level CNN is used to extract the morphological information. And if you have read some papers in the recent years, you will find most of if the paper has used the convolutional network, in most of the time, we just use it to extract the morphological information because convolutional network is very useful to do this. Yeah, so here is also another phenomenon that you should pay more attention to. This work not only use the character level CNN, they also use the word level LCM. So that means there is some complementary between the word level representation and the character level representation. If you want to improve your systems, this is a very better solution. You just can combine these two types of information together. In most of the time, you will get a better performance. Yeah, I think this is maybe the final extension of the convolutional work. We call it the structured convolution. So what does the structured convolution matter? Why should we use the structured convolution? Here is the case. Suppose we have the sentence. If we use the vanilla convolution network, if we use the traditional convolution network, we would do something like this. We just consider any case of the combination. I mean, we will consider any case of the combination of these two words. However, in most of the time, some convolution operation is not necessary. So maybe some combination is redundant. You shouldn't take it into consideration. For example, maybe the noun-verb pairs will be more informative. Other interaction, maybe you could ignore them. So another reasonable solution is apply convolution like in this way. You just ignore some not necessary edge, and you just could convert. You could compose the different word by a predefined structure. So that is the thing the structured convolutions should do. They just should predefine a structure. The structure could be tree, could be a graph, and then you apply the convolution operation over the whole graph or the whole tree. Also, in one word, that is, the structure could provide a strong prior. So there are some maybe typical research work has explored this in direction. For example, this work just said we could extend our traditional convolution to a tree structure. And this work just claims that we could extend the convolution to the graph structure. So that is the graph convolution work. I think everyone maybe know this research concept, right? Because the graph convolution network has become one of the most popular or hot topic currently. But no worry about the detail of the graph convolution network, because maybe Graham will give some detailed discussion about it. The final is a summary, as I think is something I want to sharing with you. So previously, this figure is very similar, right? This slide is very similar to previous one. So previously we have said we have a lot of compositional functions that we could use them to learn the representation of a sequence of words or a sequence of characters. We have the CBOW, we have the CNN, we have also something others. So the question is how do we make the choices of the different neural sequence models? I mean, maybe now you have a task test classification. Should we use the CNN, or should we use the graph network, or should we use the CBOW? So how could we make the choices of different neural sequence models? So to address this question, the first thing is we should understand the design philosophy of a model. I know previously some students in this class also asked the question, that is, what is the inductive bias? Here is a definition from the Wikipedia. So the inductive bias, I think, is a very important concept in the deep learning. or in the neural network field. So it is a set of the assumptions that we use to incorporate to our learning algorithm. So here the keyword is assumptions. You just apply some assumptions when you learn your models. So one typical or a special case of the inductive bias is the structural bias. It is also very frequently used term in the neural networks. So the structural bias is a set of prior knowledge incorporated into your model design. Here, I give some detailed explanation. So we could get to know the structural bias from two perspectives. The first is, I call it locality. So I mean the local and the non-local could be one type of structural bias. So the local means, suppose here is a sequence of words. The local means maybe the first word could only interact with the close number. However, the non-local means each word could interact with some maybe remote word. Maybe the W4 could interact with the W1 or even the W6. So that is the local and non-local. Another perspective of the structural bias is you can understand the structural bias from the perspective of the topological structure. I mean, your structural bias could be a sequential, or could be a tree, or even a graph. So if you have understand this, then we could make a whole picture of your design models. So for the locality bias, we have two choices: the local and the non-local. And for the topological structure, we also have three choices: the sequence, tree, or graph. So the next thing is, what if we combine these two settings? If we choose the local and the sequence structure, then we have these two models. So all you can understand is the recurrent neural network and the convolutional neural network, the inductive bias is from the locality bias, this is local. From the topological structure is the sequence. So what if we combine these two choices together, the non-local and the tree? If you combine these two together, that is our structure CLA. So why we call it a non-local? Because the different the words could be connected with some remote neighbors, and the structure is a tree. The structure is a tree with predefined beforehand. So what if we combine these two together, the non-local and the graph? Yeah. So maybe we will introduce the model in the later class. If you really want to know the answer is maybe it could be a graph network, or it could be the transformer. So what if we combine these two terms together, the non-local and the sequence? We also would introduce this neural component in the later class, and the answer actually is attention mechanism plus some sequential model. So maybe also can design some other combinations. What if the local and non-local combined with the graph network? Maybe they also have some structure could be belong to this term. I just means you can understand your neural component from the perspective based on these 2 points, and you just could make it clear about what the CNN could do, what the recurrent network could do, or what the graph network could do. Okay, I think that's the whole things I wanted to share in this class. And thanks very much. And any question? No, I will share these slides maybe on the website, and you could maybe download this.